Okay, let's start. So last time we talked about how, all semester we've been writing net accumulation functions in what kind of form? Open, right? With integral, right? So open form reflects process, but it's not helpful for computing and doing algebra. So we said, now we're going to go into a section of the course where we're going to start learning techniques for, given an open form net accumulation function, let's write it in a closed form because those are much more efficient, right? So, and we said there were two keys to that. The first key was the fundamental theorem of calculus. And the second key was antiderivatives, right? Antiderivatives. Since we have the rate function and we want the function whose rate is the one we have, well, that's antiderivative. Because to get a rate function, you take derivative. Now we've got the rate function, we want the original, so that's antiderivative. And then we said, to learn antiderivatives, you don't want to learn a whole new set of rules. What we want is, instead, we want to just know derivatives so well that we can do them backwards. So this is a list of really short, easy functions, and I want you to see in 3 minutes if you can write down all the derivatives. This is derivative, not antiderivative. These are derivatives, like what you did learn for the first time in Calc 1. So we're just going to get refreshed on taking derivatives. So given this function, I want you to find the rate of change function. Right? Take the derivative, find the rate of change function if these were like amount functions or accumulation functions. Okay, see how many you can do in 3 minutes. 3 minutes. Can anybody get them all in 3 minutes? You should. Last one is? Okay, and we're not going to take any, this is just get that memory going of derivatives. Any questions on these? Don't try to copy them all. If you're not close to copying them all down, just go to the video and look at those later for the. But any questions? So are they familiar? They should be familiar. But we gotta, like I said, if we're going to be doing antiderivatives, we gotta know our derivatives down cold. And these are the easy ones. These are just the basic rules. Okay. So then the idea is, given one of these blue functions as a rate function, do you know these derivative rules so well that you could recover the original function as its antiderivative? The black one's given. Okay? So given a blue function, could you come up with the antiderivative or the original function given or something, or like a constant multiple of that? And being able to do that's going to be really important for your efficiency and success at this. Okay? Any questions? Okay, so that would be like easy ones, right? So if you were given something like the blue one or a constant multiple of it, that would be considered an easy antiderivative to do the rule backwards, just pure memorization, and get the black one. But now the techniques we're going to learn in the next couple weeks are going to be for harder rate functions, harder ones than the blue function. And the first harder technique that we're going to learn is when you have a rate of change or a function that's the result of the chain rule. So and the same thing again, in order to kind of go backwards from the chain rule, it's a matter of really knowing the chain rule well. So that's the next practice here, is doing some chain rule derivatives. Let's do that. So here are 4 functions. I want you to take the derivative. Take the derivative again. And these are all would be using the chain rule. Using the chain rule. Okay, how'd you do? How'd I do? Any mistakes? You agree with it? Okay, so given these orange ones as a rate function, our goal in the next day or day and a half is to then recover the original function. So given that function over there on the right as a rate of change function in an open form net accumulation function, recover the antiderivative or the original function so we can write the net accumulation in closed form. So what are we looking for? So there's a key to this, right? The key thing that we're looking for what's the key to the pattern here that's going to say, yes, this qualifies as one that we're going to do like the reverse chain rule on? Something very specific about each one of these that has to be met. So what is the qualification that the function was the result of chain rule? And we can do this reverse chain rule. Yeah. Okay, so it's two terms multiplied together. So can this be anything? Could this be, or does it, what requirement does this have? Yeah. Right. So the whole key is this power right here. That power has to be what power? 3, because why? By the power rule, it has to be the derivative of what she said, the derivative of the interior, right? And so the derivative of the interior is going to be something x cubed. So if this were any other power besides cube, this would not be the result of chain rule, and we can't like reverse chain rule. We'd need something else. Does that make sense? Again, this right here has to be the derivative or a constant multiple of the derivative. It doesn't have to be exactly the derivative, but it can be any constant multiple of the derivative of what's inside here. And of course it is, because that's what we did, right? To do the chain rule correctly, we did that. But we're going to be given a function that looks like this. So we need to do this check first. We need to check to make sure one of our factors is the derivative or a constant multiple of the derivative of the interior of the other. That's this requirement that has to be met to do this reverse chain rule. Does that make sense? Okay. So so the chain rule says if you have g f of x, what's the derivative? What is the derivative of a function g of f of x? G prime f of x times f prime of x, right? Okay. So now thinking of antiderivative, it's going to look something like this. We're going to have something of this form, g prime f times f prime, and we want to recover the original function. Notice two factors collapse into one, right? So we've got this requirement, right? We said this thing has to be the derivative, or it could be any constant multiple of the derivative of this, and it would qualify. So this has to be a constant multiple of the derivative of this. And then, so now looking at what we've got there, what are we going to do to take the antiderivative? So what are you going to focus on in the rate function to recover this amount function? What are you going to focus on in the rate function? Are you going to focus on exhibit A in order to recover this, or are you going to focus on exhibit B to recover this? Exhibit A or exhibit B has the information to recover this function. So f prime, does that have the information to get g of f of x? Has nothing to do with g, right? Doesn't tell us anything about g. So, but g prime f, that has all the information to get g of f, right? Because it has something to do with g and it has something to do with f. Okay, so we're going to focus on this. What do we need to do to that to recover the amount function? One step. Antiderivative of g. So that's really it. There might be a little constant multiple mess to clean up, but the whole thing to this is identifying the g prime f part and then doing the antiderivative of g. That's like 80% of it. So what will the approach be? We're going to check to make sure we have the g prime f times f prime form. Okay? What does that mean, checking to see? It means that this thing has to be a constant multiple of what's inside the other, right? So that thing has to be a constant multiple of the derivative of the inside. And then, what we said, we're going to write the antiderivative of the exterior function of g, or the antiderivative of g prime, and we're going to keep the inside as it is, right? The f just stays f. And then, so then we're going to make an attempt, and then we're going to check it. How can we check it? How can we check our first attempt? Take the derivative, right? And there's more practice doing the chain rule, right? We're going to take the derivative, and we're going to see if when you take the derivative of our attempt, you get exactly the thing that you were given here, then we got it. But oftentimes, you'll be off by like a constant multiple, and we'll have to adjust the first attempt by just some factor, like 3 or 1/3 or 10 or pi or something like that. So that's what we call kind of cleaning up the mess. Okay, so 2 steps. Make sure we have the right form. Make sure this one is the derivative of the interior of the other. And then identify this and take the antiderivative of g prime. Check it by taking the derivative and then see if you need to make an adjustment. So let's practice here. So that's all the same stuff from the last screen. So example, here we go. X cubed plus 8x to the 4th to the 5th. Now before we get started on this, notice that this integral, how is this integral different than the ones we've seen all semester? What's different about this? No limits, right? So what does that mean? First of all, let's write out what that means before we actually attempt this problem. When you see this is called an indefinite integral. It means the same thing as this. Integral from a to x of t cubed 8 plus t to the 4th to the 5th dt. We're familiar with that, right? So by indefinite, it means it's like all net accumulation functions, and by all we mean what? Starting at any starting point A. So when you see nothing for the limits on the integral, it means all possible net accumulation functions with this rate function. How do we have more than one? Because of the starting point is this variable, right? So you could choose a different starting point. So the A makes for many possible net accumulation functions, right? That have that rate. Oh, cool, I can do the eraser on my pen. I didn't know that. So the reason there's more than one net accumulation function is because we can start at any x value, start accumulating, so that our net accumulation is 0 at any value a. So when you don't see those limits, that's what that means. Okay, so you don't have to write this out. So you can just start working on it, but just know in your mind that that's what that means. Okay, so now we're to the technique here of finding the antiderivative. And so we look at this and we say, one of those is like our g prime f, and the other is f prime. So we got to check that. Do we have, first of all, do we have this form, meaning do we have this requirement met? How is it that we have that requirement met, that we have the derivative of the interior of the other parts? Where do you see the one being the derivative of the interior of the other? Which one is the f prime? Yep, x cubed, or the t cubed, right? Because is that essentially the derivative of the inside? All that matters is the power, right? We can deal with constant multiples, factors, that's no problem. Got to have the power right. So when you take the derivative of this, the power will be cubed. That's what we got, cubed. Check. It works. Do you see that? So what are we going to focus on then to write the antiderivative? We want to focus on the g prime of f. Is that exhibit A or exhibit B? Which is the g prime f? Exhibit A or exhibit B? Exhibit B. Right? And what are we going to do to exhibit B for our first attempt at the antiderivative? We're going to focus on what? This is like g prime f, and we're going to do what? The antiderivative of the exterior, which is leaving the interior as it is. So 8 plus t to the fourth to the what? 6th. Everyone see that? Antiderivative of power rule raises the power. If we have a 6 here, we're also going to need a 1/6. Okay, so we'll call this the first attempt. We've got a shot. This is a shot at it, right? So we took the antiderivative with respect to g prime to raise the power from 5 to 6. And so now we want to check it. How do we check it? Derivative, right? We're going to take the derivative and check it. If we get exactly what we started with, then we're done. All right, so what's the derivative? 6 times 1/6. So now we got to know our chain rule, right? 8 plus t to the fourth to the 5th times 4t cubed. Now we ask, is it exactly the same as the one we started with? How is it off? There's an extra multiple of 4 that we don't want, right? When we take the derivative of this, we want to get this, but without the 4. So now we're going to adjust the first attempt. How do we need to adjust the first attempt? So that when we take the derivative, that 4 won't be there. What do we need? We need a 1/4. Also with the 1/6. You see that? If I tag on a 1/4 to this now and take the derivative, the 1/4 and the 4 will be gone, and then it will be exactly like the one we have. So we need 1/4, 1/6, 8 t to the fourth. So that's second attempt. Second attempt, take the derivative. And if you take the derivative, you'll get exactly the one we started with. 6 times 1/6 times 1/4 times 4 all makes 1. So we got our antiderivative on the second try by including the 1/4. And so now we're ready to write out using the, now that we have the antiderivative, we use the fundamental theorem to write out what the closed form accumulation function is. And remember what that was? You take the antiderivative, you plug in the x, you plug in the a, and you subtract. So I'm going to make this 1/24. So now it's going to be x to the fourth minus 1/24, 8 plus a to the fourth to the 6th. Okay, we'll pause there for a second and see if you have any questions. Any questions on getting the antiderivative or using the fundamental theorem to write out, this is now the closed form net accumulation function for that kind of set. This is like set of all possible net accumulation functions, starting at any value a. Anybody have a question? Okay, so now what is this? This is like the minus f of a, right? What kind of thing is that? If a is our starting value, say it's like 3, then that whole thing is just a number, right? It's just a number. So when you plug in a into your antiderivative, you're always going to get just a number, and that's going to be the minus f of a. So to make it, the shorthand version of that is plus c. Minus f of a from the fundamental theorem, that's the plus c. It's the subtraction factor that you need for starting accumulating at A. So then we can write 1 over 24, A plus x to the 4th to the 6th, plus C, it's referring to a constant, and that constant is our minus f of A from the fundamental theorem. So that's what the plus C means. It's just easier to write than writing the whole thing again with A plugged in. Okay, anybody have a question? Okay, let's try another example. Okay, so here's one. Now, so first of all, we'll just one more time, we'll write out what this means, and then we'll never have to do it again. What does this mean, the fact that there's no limits there? It's the integral from a to x of cos t over sine to the 4th t. Okay, those mean exactly the same thing. Those mean exactly the same thing. This is all net accumulation functions starting from any value a, whose rate function is cosine over sine to the 4th. And we know that's what that means right there. Okay, so now this one, how is this one kind of different? It doesn't really look like this, right? We're on the lookout for something like this. How does it not look like that? There's a huge difference, right? Just in visually, structurally between this and this, which is? Yeah, this is a fraction, this is multiplied. But that's no problem, right? How can we write this now as multiplied? Cosine x. You could write 1 over sine to the 4th or sine to the negative 4th. And just to emphasize, whenever you see the exponent like this, sine 4th x, it means this. You could put the whole sign in parentheses and then put your exponent outside the parentheses. You're taking, if sine x comes first, then you're raising that to the 4th power. Okay. So first thing we do do we have the requirement met for the g prime f prime form? Because why? Something needs to be the derivative of something else, right? What is the derivative of what? Cosine is f prime, the derivative of the interior, right? This is the derivative of what's inside here, meaning this came from a chain rule, right? This came from a chain rule derivative. So now what are we going to focus on? We need to find the g prime f part. Is that exhibit A or exhibit B? B again, exhibit B, right? This is the g prime f. So our first attempt will be, the only thing we have to do is antiderivative of the exterior function, right? The g prime to g. Leaving the interior as it is. So what will the attempt be? Sine x to the negative 3, right? You're going to raise power for antiderivative. When it's negative, that negative 4 raises to negative 3. Anything else we need on that attempt? Yeah, so we need to adjust for that negative 3rd. So there's our first attempt. Check it with the derivative, right? So now we're going to do the derivative to check. We're going to get chain rule, negative 3 times negative 1/3 sine x to the negative 4th times, by the chain rule, cosine x equals sine x to the minus 4 cosine x. And we ask, is it exactly the same as the rate function we started with? Exactly. Yep, it's exactly the same. We're done. So now we just have to write. Fundamental theorem says, oh, I make mistakes, so it happens. He's saying it, and it must be right. Is this better? Okay, any questions? Okay, here you go. You try this one. So, we got our g prime of f, right? And g prime is to the -1. So we raise the power up to 0, and then we take 1 over 0 to cancel out the 0. And so we got 6, and this doesn't exist, and then this all goes away because anything to the 0 is 1. So how are we doing here? Right? There's only two people that can divide by 0. Chuck Norris and my daughter. No one else can do it, okay? My daughter's done it twice, okay? But no one else can divide by 0. You can't, it doesn't exist, right? And then this is a big red flag also because 2 minus 9x to the 0, then the x's go away, right? Because you got something to the first. All right, so you got all kinds of wonderful warning flags here that you're not on the right track. 1 over 0, x is going away because to the 0 power. So you have to go back and say, something's wrong here. What is the antiderivative of something to the -1? Some of you remember. It's natural log. So this is what I was talking about. You got to know your derivatives so well that you can do them backwards. So something to the -1. To get something to the -1 from a derivative, that comes from natural log. And then you need a absolute value, and we could talk about that later. Don't have time right now. But natural log, so when you do antiderivative, you need an absolute value of the argument. What else will I need with this attempt here? Thinking about the derivative, to get back exactly this, if I took the derivative, what else will I need with this natural log? The 6, of course. Anything else? Can we just do this all in one step now? When I take the derivative of this, what's going to be different from this? When I do the chain rule, I'm going to have times, not 9, -9. I'm going to have times -9 in the chain rule. So to correct for that, I need? So I just did both attempts at once. And this is the idea that when you start getting good at this, so if you want to do 6 natural log as the first attempt, that's awesome. All right? That's the first attempt. Then you come back here and you do the derivative, and you get 6 times 1 over 2 minus 9x. But then by the chain rule, times. So can you anticipate that in your first attempt? Can you see that? No, -9. Can you anticipate the chain rule of getting that -9 and then just correcting it for it in the first attempt? That's the goal. So -2/3 natural log of 2 minus 9x plus c, which is the, reminder, the minus f of a in the fundamental theorem. Okay. Did I lose you? If I lost you, can you ask a question? Anybody? Yes, please, Adam. Well, even though it's in the absolute value, still taking the derivative of the interior. So the derivative is still -9. See that right there? Even though there's absolute value now, you're still taking the derivative of the inside, which doesn't, that absolute value doesn't apply. Is that what you're getting at? So we still have that factor of -9, so we need a -1/9. Other questions? Yes, please.
Just wanted to confirm that the reason why we don't mess around with 6 is just because it's just a coefficient.
Yep, right. You remember when you took derivatives and you had a constant multiplied by a function? It just always came along for the ride. So antiderivative is the same thing. They just, any constant multiple that's multiplied just comes for the ride and stays there. Yep. Other questions? Okay, one more example and then we'll take the quiz. Okay, so this is another way to write arctangent. So I'll just write it the other way so you see it both ways. So this is the same as arctangent times 1 over 1 plus x squared. So first, we're going to check for this form. Do we have g prime f times f prime form? Meaning, do we have the derivative of another function in here somewhere? What's the derivative of what? So you want this to be the f or the f prime? Okay, there's up there in the front, they're saying this one on the right here is f prime. Agree? That's the derivative of arctan, where arctan is the f. Okay, but where's the g? Where's the g prime? So it's there, but it's implied and not explicit, right? It's implied. This is f of x, right? But then where's the g prime? Arctangent. What power is it if there's no power? Isn't it 1? Isn't it arctangent to the first times the derivative of arctangent? So how do we do that? So our g prime is to the first power. Antiderivative to the first power is to the second power, right? Antiderivative of something to the first power is raised power. And then what we also need for the 2? 1/2. Derivative of this, there won't be anything else that, there's no more mess to clean up, right? 2 times 1/2 is 1. Arctangent times the derivative, 1 over 1 plus x squared, done. So that one's a little tricky because you got to see that this is implied to the first power. That to the first power, that's our g prime.